In the vast universe of biological research, scientists are often looking for tiny clues. These clues can help us understand diseases, develop new drugs, and even track down criminals. One of the most powerful tools in this quest is the ELISA. ELISA stands for Enzyme-Linked Immunosorbent Assay. It's a mouthful, but it's really quite simple. ELISA is a test that detects and measures substances. These substances can be proteins, hormones, or even viruses. Imagine you're a detective looking for a specific fingerprint at a crime scene. ELISA is like dusting for those fingerprints, but instead of dust, we use antibodies. Antibodies are special proteins made by our immune system. They bind to specific targets like a lock and key. In ELISA, we use these antibodies to find our target molecule, our fingerprint, in a sample. ELISA is widely used in many areas of biology and medicine. It's used to diagnose diseases like HIV and cancer. It's used to test for food allergens and to ensure the safety of blood transfusions. ELISA is a versatile tool that has revolutionized the way we study and understand the microscopic world. So how does this elegant technique actually work? Let's dive in and explore the fascinating world of ELISA. The beauty of ELISA lies in its simplicity and specificity. It all starts with an antibody that specifically recognizes our target molecule. This antibody acts like a molecular homing beacon, seeking out and attaching itself to the target. But how do we see this interaction? This is where the enzyme-linked part of ELISA comes in. Attached to our antibody is an enzyme. This enzyme acts like a tiny signal flare. When we add a specific substrate to the mix, the enzyme springs into action. It modifies the substrate, causing a detectable change, often a change in color. Imagine the enzyme as a tiny artist carrying a paintbrush. The substrate is like a blank canvas. When the enzyme encounters the substrate, it paints a colorful signal telling us that our target molecule is present. The intensity of the color is directly proportional to the amount of target molecule in the sample. This elegant color-changing mechanism is the heart of ELISA. It allows us to not only detect the presence of a target molecule, but also to measure its quantity. It's like having a molecular ruler that tells us exactly how much of something is there. To perform an ELISA experiment, we need a few key ingredients. Think of it like baking a cake. You need the right ingredients in the right amounts to create something delicious. First, we need our sample. This could be anything from blood serum to a food extract, depending on what we're testing for. Next, we need our trusty antibody, specifically designed to recognize our target molecule. Then comes the plate, a special plate with multiple wells. Each well acts like a tiny test tube where the ELISA reaction takes place. We also need a washing solution to remove any unbound molecules and prevent false positive results. Finally, we need our enzyme-linked substrate duo, the color-changing artists of our experiment. The substrate should be chosen carefully to provide a clear and easily measurable signal. With these essential ingredients in hand, we're ready to embark on our ELISA journey. Let's move on to the step-by-step process of this incredible technique. The ELISA Protocol, much like a well-choreographed dance, involves a series of carefully orchestrated steps. Each step builds upon the previous one, leading us closer to our answer. First, we begin by coating the wells of our ELISA plate with an antibody. This antibody will capture our target molecule from the sample. Next, we introduce a blocking solution. This step is like placing do not disturb signs on any unoccupied surfaces of the well, preventing non-specific binding and ensuring accurate results. Now the star of the show enters the stage, our sample. We add a measured amount of the sample to each well. If our target molecule is present, it will bind to the capture antibody. Time for a quick rinse. We wash the wells to remove any unbound molecules, leaving behind only those specifically bound to our capture antibody. Enter the detection antibody linked to our enzyme. This antibody will bind to a different part of the target molecule, forming a sandwich-like structure. Another wash ensures that only the specifically bound detection antibodies remain, minimizing background noise. Finally, the moment of truth. We add the substrate, our enzyme's canvas. If our target molecule is present, the enzyme will spring into action, transforming the substrate and producing a color change. We measure the intensity of the color change using a spectrophotometer. The intensity directly correlates to the amount of our target molecule in the sample. This elegant dance of molecules and washes culminates in a simple, easy-to-interpret signal revealing the presence and quantity of our target. But ELISA is not a one-size-fits-all technique. Let's explore two of its most popular variations, direct ELISA and indirect ELISA. Direct ELISA involves an antigen being directly attached to the plate. Then, an enzyme-linked antibody specific to the antigen is applied. This method is quick and reduces cross-reactivity, but it might be less flexible. Indirect ELISA, on the other hand, uses a primary antibody that binds to the antigen, followed by a secondary enzyme-linked antibody that binds to the primary antibody. This method increases sensitivity and flexibility, though it can be more time-consuming. ELISA is a powerful tool in diagnostics and research, offering high sensitivity and specificity. Its versatility allows for the detection of a wide range of antigens and antibodies, making it indispensable in many scientific and medical applications.